Hello, so continuing the last day, we're looking at these first few HL topics in probability and statistics, and today I want to kind of come back to some of the ideas of what degrees of freedom are, as well as reminding about various the tests and distributions we've looked at before. This question's all going to be based on this table here, which is meant to be data from 1,000 students across a province, their grade 10 performance in a numeracy test, and we can see their scores broken up here, up from 0 up to 90, the frequency of them. That's it. This is a sample of 1,000 students from a province, from all the grade 10 students. So in this case, what is the population from which this data is sampled? The population is all grade 10 students in the province. And so everything we're looking at here is a sample of the entire population. Now that said, from the sample, we can now estimate the mean and standard deviation. And for that, we'll use our GDCs in a bit, but we'll need to, if we look at this data here, for example, the range from 0 to 20, we want to just find the midpoint of each. So we'll have a 10 for that, 25, 35, 45, 55, 65, and so on. And using those midpoints and the frequency, we can estimate the mean and the standard deviation of this data. And keep in mind, I don't actually know how many of these 22 were exactly at 21 or 22 or so on. I just have this sort of range for each, and hence I'm using those midpoint values. That's it. That should be pretty quick. We've done those things before. If you do that for the mean, we should get approximately 50.19. And for the standard deviation, we should get approximately 10.342. Now, keep in mind, even if I did use the actual data of all the exact scores for these 22 students, the exact scores for these 137 students, even if I had all that data, this mean and this standard deviation would still be estimates, because if I had all that data, you may think that's exact, but that's just based on the sample of 1,000. And if we're trying to draw conclusions about the entire population, which is all the grade 10 students in the province, we are estimating. No matter what we're looking at, unless we're literally finding the data for every single student, this is a sample. So no matter how much data we look at from the sample, it is still an estimate. These are all estimates of the actual population. Hence, it's always important to think about what is the population we're looking at here. So with that said then, we want to perform a goodness of fit test to check whether this data comes from a normal distribution, as is claimed by the province's educational ministry, with a 5% significance level. So the null and the alternative hypotheses. So the null hypothesis is the status quo, essentially in this case that the province is correct, or that the data is normally distributed or follows a normal distribution. That's the null hypothesis. The alternative hypothesis is that the data is not normally distributed. I'll just kind of squish that in there, feeling a little bit lazy. All right, so now to determine this. First, if we wanted to perform a goodness of fit test, we need to compare the observed results with the expected results, assuming it is, in this case, a normal distribution. So for this, first, I need to find the probability, assuming it's a normal distribution, that there would be a score between 0 and 20, 20 and 30, and so on. And so for that, I'm going to use my estimated mean for the population, which was again approximately 50.19, and my estimated standard deviation for the population, which was approximately 10.342, if I can read my own writing. Yep. And I would then use the cumulative probability distribution function that we've used earlier for a normal distribution, and determine what's the probability if we have a mean of 50.19 and a standard deviation of 10.342. What's the probability that a result would be between 0 and 20? And that probability, which again we've learned in earlier lessons, your GDC can perform that quickly, should come to be 0.00175. That said, once I know the probability of a score between 0 and 20, then keep in mind I am looking at 1,000 students. So I just need to multiply that by 1,000 to find the expected number of students. Multiply that by 1,000, we get 1.75. I want to do the same idea for all of these. So using the same mean and standard deviation, which again are estimates, we want to find the probability that there'd be a score between 20 and 30, and we get a slightly higher probability, 0.0237. Multiply that by 1,000, you get 23.7 expected students to have a score between that. Again, assuming this really is a normal distribution. Now, this takes a little bit of time, so I don't need to read everything out. So I'll just write out first all the probabilities. Again, wrote those all the three significant figures, multiply them all by 1,000, we get these values. All right, so now, before we go on, if we want to perform any chi-squared test, we need to make sure it fits the expected count condition, which means the expected values need to be above 5. And I can see right here we have a problem. That expected count there and that expected count there from those two columns is not more than 5. So I shouldn't yet perform my goodness of fit test. And I can take care of this fairly nicely by just combining. For example, I'll just merge these two columns and I'll merge these two columns. And so instead of going from 0 to 20 and then 20 to 30, I'll go from 0 to 30. And over here, I'll go from 70 to 90, which means I'll look at, and all I really need at this point is the observed and the expected. So 22 observed. And if I add these together, I get 25.45 expected for those. Merging the last two, I have 26 observed, and my expected is 27.61. All right, excuse my messiness there. Now I can actually perform my goodness of fit test, but first I need to figure out what the degrees of freedom are. For a goodness of fit test, the degrees of freedom are the number of categories minus 1, so n minus 1. But then also, because we are estimating some parameters, minus the number of parameters we've estimated. And in this case, there was two parameters necessary. There's two parameters necessary for a normal distribution, the mean and the standard deviation, both of which I did estimate. Again, those are not the exact values for the entire population. Those are estimates of the entire population based on the sample we took. So it's n minus 1, which we've learned earlier for the degrees of freedom. But since now we're looking at some estimated parameters, we subtract the number of those estimated parameters, in this case 2. And so n being the number of categories, which remember I've merged these. So I have 1, 2, 3, 4, 5, 6 categories. Minus 1 minus another 2. So the degrees of freedom for this equals just 3. And changing the number of degrees of freedoms can make a pretty significant difference to your overall results. And before I actually finish this off, I'll just kind of go back up to my notes here. In general, I have some points here about what R would be, the number of estimated parameters, depending on the type of distribution we're looking at. And right now I'm focusing on a normal distribution. So I have 2 estimated parameters. All right, now though, I can complete my hypothesis test. I have made a huge mess of my table, but I need to just compare these observed values with these estimated values. And when I do that, which we've learned about before, and with the degrees of freedom of 3, we should get a p-value of approximately 0.200. Which means, again, we can imagine that If this data is if this data is part of a normal distribution, we'd expect to see these observed values roughly 20% of the time, which is significantly more than the 5% significance level, which means we do not have nearly enough evidence to reject our null hypothesis, so we fail to reject H naught. And again, we don't say we accept it, we say we fail to reject it. Again, it still may not be normally distributed, but we don't have really nearly enough evidence to show. All right, and again, keep in mind, H naught was that the data is normally distributed. That was H naught. I don't need to write that down. I've said it already. Okay, keep in mind, I did gloss over a lot of the actual GDC work because we've done that before. Once we are aware of that, a lot of this is fairly quick.